In this video, we will train a convolutional neural network that will be able to identify radar image patches that show ships. For this, we will use training data coming from the European Sentinel-1 satellite. We will use small grayscale image patches of 64 by 64 pixels that show ships and label them with a class 1. Then we also have image patches that do not show ships, as we want our model to learn what not to identify as a ship. Those patches will receive the class 0, making it a simple binary classification problem. In the next part, we will then apply the trained model on a large-scale image to detect, count, and highlight ships with a moving window approach. But let's start with the network itself. The imports that are already listed are libraries that we discussed before, so I will not go into detail here. But I would like to add two more imports that are new or have a specific role in this use case. First, from pill, import image. Pill is the pillow library which can open and handle image data like JPEGs or PNGs. We'll use this image class to open the image patches. Then we need several layers from Keras and load them with from TensorFlow.keras.layers, import dense, dropout, conv2d, flatten, and MaxPooling2d. So importing conv2d, flatten, and MaxPooling is not different to any other layer we got to know. Now we should devote ourselves to importing the data. We have a total of over 3,000 image patches that need to be loaded and processed before we can push them into the model. Loading this number of images manually is obviously an impossible task. Therefore, we will create a function with which we can load the images automatically. We'll work our way through the function bit by bit so that everything is understandable. First, we define our function and give it the name readImages. Then we only need a single parameter for the function, which will be the folder path where the images are stored. We then set a variable called files, which will store all the file names that can be found within the path that is given. And OS, which we have imported up here, has a function that can exactly do this. We say os.listDir and provide the path that we set as a parameter. Let us check what is actually stored in the variable files. So we print it and call the function with the folder path of the ship images. They lie in the subfolder data and 00_ships. Let's execute the cell. And you see that we got a very long list with all the file names that are in the given folder. We can use this information that the variable files holds a list of file names to iterate over the list and open the individual files. So we set up a for loop with for file in files. We could also use any other name instead of file, but I think this is quite suitable. Then we could directly open each file, but as you haven't created the data by yourself, you cannot be sure whether the folder only contains images and not something else that would throw an error when Pillow tries to open the file. So we should set up some kind of filter to make sure that only PNG files are used. I will implement that with an if statement. If the file ends with .png, we will consider it to be opened. And we do that by setting up a variable image that holds the opened file. And to open the file, we use image.open. And now we need to provide the file as well as its path. Currently, we either have the path or the file name, so we need to combine both with os.path.join and provide the path first and then the file name. Now a file is opened as a pill image, but as our model would like to have an array, we should turn it into one by overwriting the image variable and say np.array from the image. Now it's time to check the shape. You should always do this after opening data, as various libraries might open the data with the dimensions in a different order. So I add a print statement with the shape of the image and add a breakpoint so the loop gets stopped after the first file. You see that the order of width, height and channels is correct, but we have 4 channels even though our radar image is just in grayscales. In this case, this is due to the way a PNG stores data. It uses a red, green and blue channel and an alpha channel to store transparency information. As red, green and blue store the exact same information in our case, we can just select the first channel to reduce the amount of data that we load into the script. So I add a slicing operation that keeps the full width and height, but selects only the first channel. And I use a colon 1 instead of index 0 to keep the extra channel dimension. If we check the shape again, we see that we only keep the first channel. Now we are able to open each image as an array, but currently the image is just overwritten by the next image. Therefore, I want to save the opened image within a list. I add a variable images in front of the loop and set it up as an empty list. Then I add each opened image to this list with the append command. As a last step, I want to return that list, but as the data type list is nothing I can push into the model, I will return it as an NP array. Let me clean up this function a little bit by removing print statements and the breakpoint, so we can actually deploy it to load our data. We will now use our function 2 times to load the images. First, we will use it to load all images from the ship folder and save the loaded images behind the variable ships. Then I repeat this for the images that do not show ships and save them behind the variable no ships. It will take some seconds until all images have been loaded. As soon as this is done, we should take a look how many images we've got and print the shape of those 2 variables. We have got 1,784 images of ships and 1,800 without ships. And the rest of the shape looks good as well. If you would like to see how the data looks like, you can make a simple plot with plt.emShow and take any position from the ship or no ship array. Next, we want to combine the array with ships and the ones without ships into a single X dataset. And we can simply do this with np concatenate. And provide those 2 variables as a list. I will provide ships first and no ships second. Now both arrays are concatenated along the first axis, meaning we first have 1,784 samples of ships and then 1,800 samples of no ships, resulting in a sequence of 3,584 images. However, this is only 1/2 of our training data, as we still need the corresponding Y data, which should be the classes 1 and 0. First, I will deal with the class 1 for the images with ships. I set up a variable Y ships and use np.once to create the label 1 for each image that shows a ship. And to do that, I provide the length of the variable ships as an argument so that NumPy creates 1784 times the number 1. Then I take care of the class 0 by setting up a variable y no ships and use np.zeros to create a lot of zeros. And to get the right amount of zeros, I use the length of the variable no ships. Now all I have to do is to concatenate those two variables as well, which will be our y data. It is very important that the order of y ships and y no ships is the same as we used for our x data. Otherwise the labels will be mixed up and we will get a hard time training the model. As we have our x and y data, we can now do a train test split. I will just copy this part as we have done it several times now. It is very important that the shuffle is set to true as the data is currently perfectly sorted. Let us now approach the topic of the CNN setup, but I would like to take a closer look at the setting of a single conv2d layer before we get to a whole model. For that I need some test data, and I will use np.random.randn to set up some random values which have the same dimensionality as our original data, with only a single sample, a size of 64 by 64, and one channel. Then I need a single conv2d layer that I store in the variable conv. Then I get the layer itself and set the number of filters to 32. The kernel size to 3 by 3 as a tuple for now, which indicates the size along the x and y axis. Then strides of 1 and 1, meaning that the filter moves one step along the x and y axis at a time. A padding of same, which triggers a border around the image, as I explained earlier. Then a ReLU as an activation function. And finally, an input shape of 64 by 64 and a single channel. In order to push our test data through this single conv2d layer, we call the conv variable, then provide the test variable in round brackets, and as we want to observe the shape of the output, we call .shape on that. With the current settings, the shape along the x and y dimensions does not change. You see that in front of the size, the word tensor shape is written. In neural networks, the type of arrays that are passed through the model are actually tensors. Tensors do the same thing as arrays, but are more efficient since we can deploy them on GPUs for faster processing. In this case, the tensor has got a size of 64 by 64 and 32 filters or channels. If I set the strides to 2 times 2, I halve the size of the tensor. That's because values are skipped while the filter still returns only a single value per position. Let us also change the padding to valid. Then it even gets smaller as we are missing the border of zeros around the input image. If I then increase the size of the kernel to 9 by 9, the larger filter will again cause a smaller output tensor. You should play around with different settings to see the effect they have on the output of this layer. Now let's start with the actual model and start with a normalization layer. I use the variable layer once again, call an instance of normalization, but this time I have to provide an input shape, so the normalization is done correctly. I will just hardcode the dimensions this time to save some time. Then I set up a sequential model, add the normalization layer to the model, and start with the first conv2d layer, which is added the same way as all the other layers that we got to know. The first argument will be the number of filters, for which I will use 32 again. Then we should define a kernel size, which we can do as a single integer or as a tuple with the x and y dimensions of the filter. If we only provide a single integer, the integer will be used for x and y dimension. By using a tuple, it would be possible to use different sizes for the dimensions, but this is usually not done. I will use a 3x3 kernel for our network. Then the stripes, which could also be an integer or a tuple, but as I want the step size of the window to be the same in x and y directions, I just use a single integer of 1. This is also the default value, so I actually do not need to provide it in this case. Then the padding, which I will set to same for this layer. As I said in the previous video, the combination of a stride of 1 and a padding of same results in an output with the same size as the input. Then we provide the activation function, which will be a ReLU for now. As we provided the input shape already in the normalization layer, we do not need it here again and can go on with the next layer, which will be a MaxPooling. Again, the MaxPooling downsizes the tensor, and as the default stride is 2, we receive a tensor with half the size of the input. After the MaxPool, I would like to reduce the risk of overfitting and add a dropout layer with a rate of 20%. Then I just copy the whole block of layers and paste it below. Now I just apply a couple of changes, like using 64 filters instead, and use a valid padding this time. By setting the padding to valid, no border will be generated and the resulting tensor will be smaller than the input. I think that 2 blocks of convolutional layers are enough for now, but feel free to add more if you want to. Next, I want to generate a single output as a prediction whether a ship is in the image or not. But as I cannot feed the dimensions of a convolutional layer into a dense layer, I need to flatten it first. So I add a flatten layer for which I do not need any arguments. After that, I can simply add a dense layer with a single neuron and a sigmoid activation function, as we have a binary classification problem. As we have done the training part several times now, I will just copy it. We will use Adam as an optimizer under a learning rate of 0.001 and use a binary cross-entropy loss function. What might be new is the summary, which will just print the model architecture. The training then uses xtrain and ytrain, just 10 epochs and a batch size of 8. Feel free to change those parameters to your own ideas. However, I will just leave them as they are and just train the model. Within the model summary, you can see the architecture and the trainable parameters per layer. The first convolution layer has got 320 parameters coming from a 3x3 kernel, making 9 parameters plus a bias, so 10 parameters, and then 32 channels. The calculation for the following layers then gets more complicated, as we not only have a single input channel, but several. After a couple of minutes, the training is done and the model reaches a good accuracy from the first epoch and improves a little bit over the time. I will add the plot to visualize the training. Then I evaluate the model to check if there are too large differences between the training and the testing dataset, which might indicate overfitting. So model.evaluate on X train and Y train. And the same on X test and Y test. In my case, the difference is not too large, and I will just leave the model as it is. Then I copy some code that can make single predictions. We can provide an index under the variable feature, which is then picked from the test dataset. The real class is shown, and then the model makes its prediction while we also plot the image. Under the index 10, we do not have a ship image, and the model also makes a prediction close to 0. If I change the index to 5, I receive an image of a ship, and the model also indicates that this is a ship. So the model does not seem to be that bad, and that's why I want to save the model, to be used in the next video in which I want to use it on a larger image. To do that, we call the model, say .save, and provide a meaningful name, like ship detection model, and add the file ending h5.